In this lecture, we will go a little bit beyond our last conversations. We'll look a little bit at the history of climate change, and we'll talk a little bit more about the Industrial Revolution, greenhouse gases, and again, the warming potential of different greenhouse gases. So as you know, we all talk about global warming, climate change, all of these things, but some people say, how can I understand climate change when I'm having the coldest temperatures that we've ever had here in the winter, or we're having a cold summer? So what is this interaction that we see between weather and climate? Often you'll hear people say, it's freezing today, where's the global warming? And so a lot of it comes from misconceptions and not understanding overall trends. And when we look at weather, weather is how conditions change from day to day or even year to year. Climate is the long-term average of weather over many decades. And changes to climate can lead to changes in weather. There was, back in the early 2000s, there were quite a few folks who started this idea that we were in a cooling phase. And so what ended up happening there is they took some really extreme data points and they drew a new line and said, look, we're actually cooling, not warming. So I want you to be prepared for this in case you ever face an audience where they say, you know what, back in the 2000s, they said everything was cooling. And also back in the 1970s, there was also a time where people said, no, we're looking at a cooling trend, as they looked at the trend from here to here. So the one thing that you have to always remember is look at long-term records, always tie people back to the data, and have them understand why there's oscillations, what are the different things that contribute to these oscillations, and what is the overall trend that we're seeing. And the overall trend that we're seeing is really that we do have this warming occurring. When we, again, correlate climate and weather, one of the things that we can look at is hurricanes over time. So just to look at any anomalous year is a bit challenging. For example, in 2005, there were actually 28 named storms, which is the most ever on record. And so some people, who really go down the cataclysmic slope, we're like, oh my gosh, this is what we have to come. Every year there's going to be more than 20-some named storms, and that's not what we saw, right? So as we follow this trend further, what we see is that there are ups and downs, there are some peaks and valleys, and there's different things that contribute to this. Not only do we see weather contributing to this, but we also know that the thermohaline circulation loop, or the AMOC, the Atlantic meridional, I can never say that word, meridional ocean current, and all these things affect greatly the warmth of the water and therefore the heat available for these storms to gather. And then we also have El Nino events and things like that, which also affect those areas. And so there's a lot of interactive effects that we have to consider. But again, with hurricanes, what we do see is that the number of hurricanes and the severity of hurricanes over time is increasing slightly. It's not as marked a trend as temperature increases, but it is something to keep an eye on. And as we know, even this year, there were some fairly devastating hurricanes last year. The really devastating ones, Maria, that hit a lot of the Caribbean islands, including Puerto Rico, and folks still recovering from that. When we think about what hurricanes draw their energy from, they draw their energy from deep below the ocean surface, up to depths of even 2,000 meters, scientists have found. And the temperature at these depths are measured by the ocean heat content, and that's a metric that has really soared by 1980. So remember when we're talking about that North Atlantic deep water, the deep water that is flowing up the Gulf Coast, following the Gulf Stream up to the areas near Iceland and Greenland, and then subducting and going down to form so much of the ocean water column. So for years, as that water has been warmer and warmer and warmer, it's been cycling down and carrying some of those slightly warmer components to it. And then you also have the heating from above. And so overall, what we're finding is that ocean heat content is actually increasing. And as ocean heat content increases, there's more energy or fuel for these storms. And so with hurricanes, there's a whole bunch of interactive effects, but a lot of it comes back to temperature, evaporation, and the ability for these storms to build and build and build and gain more energy from doing so. To give you an idea, so this figure here that we're looking at, So the figure is titled In Hot Water, and it says global ocean heat content change relative to the 1955 to 2010 average. And we have the darker blue line, which is the yearly average, and we have the 3-month average line, which goes up and down and oscillates a fair amount. And so the general trend is the darker blue line. What we see is that the ocean heat content has increased significantly. So whereas before we were looking at temperature increases that were very minor, this is a really significant increase. So significant that the ocean heat content energy, to give you an idea, the amount that we're seeing is about 1 billion times the energy of the atomic bombs used in Hiroshima and Nagasaki in 1945. Okay, so huge amounts of energy in the ocean, leading to these high levels of ocean heat content. And if we look at all the energy contained in all the world's fossil fuel reserves, it's not even a fraction of where we're at with ocean energy. So we're talking about huge amounts of energy, huge abilities to affect climate, weather, and all of those components. We also often talk about global warming, which can have, again, confusing connotations for folks. Sometimes I've said to people global weirding, and one of the reasons is that we do get weirder and weirder weather. So as we're getting these stronger storms, they become more unpredictable. We're seeing more drought in some areas, more flooding in other areas. My favorite new term within the last 10 years is thunder snow. We never had thunder snow before. And then even simple things like in Canada, for example, we've had snow in April where we usually wouldn't have snow. And a few years ago, we were wakeboarding on Christmas Eve. So, whereas, right now there's probably many feet of ice on the Ottawa River. So lots of variability in this kind of global weirding piece. One of the challenges that weather folks are having right now is all of the models are built on historical data, historical weather patterns. And as global change is happening, we're having changes to global weather patterns. So the models are actually much more inaccurate now than they used to be. So there's actually a brand new model that you can always look up. I actually found them through Facebook. They are Instant Weather, and they also are the ones who do the Ontario Tornado Watch. They have a model that is much more tightly linked to modern changes in weather, and their model seems to be more accurate than a lot of others. So if we look at some other models that look at longer term projections, there's even different pockets where we're anticipating have what we call a warming hole. So there are areas that are not predicted to increase their overall temperature as much as other areas. So one of the areas in the US that we see the warming hole is kind of in the middle of the country there in a lot of the agricultural states. And so that's actually highly beneficial for a lot of them. We also see, so here's an example, in 2010, we saw temperatures that in the middle area of the states were the record coldest temperatures that they had ever seen, whereas in other areas they were seeing temperatures above normal. So again, you've got these different pockets of weather that are not following regular trends. And again, a lot of this comes back to this whole idea of these spatial differences in warming. So as we've talked about before, we have these spatial differences which lead to, especially the poles, increasing in temperature much more than we see at mid-latitudes. And then we also see that in some desert areas and equatorial regions, there's some real increases in temperature as well. And we also talked about Pakistan and all that kind of stuff when we were talking. Oh, maybe we haven't. We will be talking about Pakistan and those areas as being areas that are going to be highly affected by climate change. We also know that rainfall patterns are shifting. So if we look at the increase in annual number of days of rain, there are some areas in the country which are seeing minor increases, and other areas in the U.S. that are seeing much heavier precipitation than they usually would have seen. If we look at the major floods per decade, I like this graph because it really lets you look at the different countries and things like that. We are definitely seeing more floods than we have seen in the past. Now, this can be caused partially by climate change, but there's a lot of other components to this. So flooding also has to do with our overall water use, what is urbanization, how is forestation or deforestation having an effect on watersheds and all these types of pieces, right? So there's a lot of different things that we're doing to modify the local environment, which may actually have relatively huge impacts on flooding. And in particular in Asia, we know that there's been a ton of flooding in India. And so there's actually a huge river interlink plan that India has proposed. It's a multi-billion-dollar plan to link up rivers, create canals and reservoirs so that they can limit the loss of life from flooding, and they can make sure that they retain water in all different areas so that they can have, effective agriculture and all those types of components. So a lot of time when people talk about extreme events being responsible, like climate change being the driver of the extreme events, one of the things you have to go back to is there's a lot of other interacting factors, but it's definitely a factor that is contributing to these challenges. Wildfires, again, is a major one. If we put the wildfires that we've been seeing recently on this graph, we would see wildfires in America go up even more. And it's been a major challenge as we've seen a lot of drying of forests in a lot of areas due to localized droughts, especially in California and things like that. We also know that the global change is not being driven by the sun. For a while there, back in the 1950s, people said, when we look at the sun's solar cycles and its magnetic field and these different components, it actually looks like overall temperature increases could be because of the sun. But what we see is that as we move into another period where we're actually moving farther away from the sun, we get less energy from the sun, and the magnetic field is also waning, our temperatures are still increasing drastically. In fact, we are actually moving farther away from the sun, so we should actually be entering a cooling phase instead of a warming phase. So as we move on and consider global temperature curves, one of the things that we keep talking about is that we are really concerned about 0.5 or 1 degree increase in temperature. But a lot of the models are actually projecting these types of increases. We're projecting 2, 3, 4 degrees Celsius increases if we don't stop emitting greenhouse gases the way we are. So when we look at a couple scenarios, here's a few different scenarios. So the red line here is the scenario that we're currently following the most. So these are fossil fuel emissions, looking at how fossil fuel emissions are either abated or we have sequestration of carbon. So if we have that, then we'll be at some of these like lower scale emission scenarios, the B1, B2. The A1, A2 scenarios are more the business as usual with some cuts and reductions. And we have not been doing a good job at even getting to A1. But the next couple slides I'm going to show you talk about how we will be affected from a weather perspective as we see these climate changes. Okay, so if we look at the number of heat days, and heat days are the number of days over 100 degrees Fahrenheit in the US, what we see is that between 1961 and 1979, the only areas that had like numerous days over 100 degrees Fahrenheit were Arizona and some areas in California. Now, if we look at different models, under the B1 model scenario, so B1 is the blue line here, so it's a scenario that calls for much fewer emissions. Under the B1 scenario, by 2070, we would still see an increase in the overall number of extreme heat days. And again, those are days that are over 100 degrees Fahrenheit. Now, if we look at a model simulation similar to the track we were trending on, here's what it would look like. So we would have extreme heat days across the entire US and Canada. So again, these are days over 100 degrees Fahrenheit. And with this, we would have a lot of challenges. We would have challenges with agriculture, potentially drought, although some areas may have more precipitation. We would have, human illnesses and deaths due to heat, real challenges for livestock with these high temperatures. And it's a very serious situation that we could be facing. When we look at Illinois, I picked Illinois as an example because actually Illinois' climate ends up being quite similar to southern Ontario many a time. And if we look at what it will feel like in Illinois or southern Ontario, by 2095, in the winter, we're going to feel like we're basically similar to the temperatures that you would see in northern Texas. And by the summer, we're going to see temperatures that we would see in the summer in Texas. So to give you an idea, like pretty major climate shifts, pretty major weather shifts, which would have, far-reaching impacts on everything that we do, from the amount of energy that we consume to cool, to the amount of irrigation needed for croplands and all of that. Speaking of croplands and areas affected by drought, the next thing I've pulled up here is looking at some drought modeling. So when I run the drought model, between 2010 and 2029, what we see is that there are some areas that are actually going to become wetter and some areas that are likely to be have more time in drought. Although the percentage of change is not significant between 2010 and 2029. But again, this is under the A1 scenario. As we go beyond 2040, what we start to see is more time in drought in some areas, and again, wetter instances in other. And in Ontario in particular, we're looking at minor drought, so getting somewhat drier. But by the time we move to 2080, what we see is this huge increase in drought sweeping across the US and Canada and providing us with numerous different water challenges that we did not have before. And this would have, again, far-reaching implications for agriculture. We would have to obviously have a lot more irrigation to be able to continue to have business as usual. And again, this would potentially lead to a lot of different food scenarios and challenges that we would have. So throughout the rest of the course, what we're actually going to do is we're going to start to look at case studies. We're going to look at different industries and see how they play into climate change, how they're affected by climate change, and how when you bring everything together, what is the full picture of climate change on the business community, as well as for ourselves. And the goal here is that you, as a consultant in sustainability or somebody who's driving sustainability initiatives in companies, can be a well-informed, well-rounded expert understanding the science behind what we see happening with climate. All right, well, I hope you enjoyed lecture this week, and I'll see you next week.